This is lecture 26, the next to last one. We're going to begin by looking at problems that lie beyond the NP-complete problems, and then we're going to loop back and consider techniques for dealing with NP-complete problems.
Some problems don't belong to NP. There are lots of problems that don't belong to NP. In fact, there are some that are known to be so hard that it's impossible to solve them with a computer. Okay? You talk about problems like that in the CS4100. But I'll give you one example here. This is an impossibly hard problem. You can prove that there is no way to write a program to solve equations of that form. So the idea is, these are called Diophantine equations. It's just polynomials and multiple variables, where all the variables and all the coefficients are integers. Okay? So the idea would be you've got to find an x and y and a z, which are integers, that you can plug in there such that the equation is solved, or report the equation can't be solved. Now, at first look, you wouldn't think that's an impossible problem to solve. Yeah?
Well, I mean, it seems like you could verify this problem in polynomial time.
Okay, could you? Okay, so that's a good question. Why is it not a member of NP? Why can you not verify polynomial time? Yeah?
That answer could be irrational, so the input would have to be pretty big.
Well, no, the answer can't be irrational. The answers have to be integers. Yeah?
Given that x, y, z, you can...
Sure, given an x, y, and z, you can plug in and see. So why is this not a member of NP? Yeah?
Because you can't reduce it down. Or, wait, no, that would be...
Right. What's the catch here? I mean, surely if someone gave you an x, y, and a z, you could plug it in and see. Yeah?
Is it because the solution isn't unique to the instance?
It doesn't have to be a unique solution. You just have to find a solution. Okay? Yeah?
Is it because the verification is faster than polynomial time?
No, not that it's faster. Yeah?
Is exponentiation for large numbers not polynomial time?
Well,
Or not exponentiation, but the actual, like,
I mean, yeah, all the exponents are going to be constants, and so, you know, the exponentiation of the time is proportional to the size of the number. Yeah.
it's possible that the only solutions are so big you can't find them.
Well, no, it's not that they're so big you can't find them. The solutions may be gigantic integers. The verification algorithm has to run in polynomial time, where the size of the problem is, you know, the number of bits it takes to describe the equation. So you can have really small equations with gigantic solutions, where the numbers are, say, trillions and trillions of bits. Yes, you can verify, but the verification takes longer than polynomial time, because the numbers are so much larger than the equation. Yeah?
But isn't n the number of bits?
Yeah, n's a number of bits.
So then...
So it would take, I don't know how many bits it would take to describe that equation, not many. Right? I mean, we could just describe it in ASCII. Let's say 8 bits per symbol. So take the number of symbols times 8. You could certainly describe the equation in that many bits. Okay? But the solution, proposed solution, might be dwarf in, could be exponential in. You know, the solution could be arbitrarily large, and so large that you can't. Yes, you can verify it, but the time it takes is all out of proportion to the size of the equation. Yeah.
What happens if there's no solution?
Well, if there's no solution, that's a possibility, but you don't have to have a verification argument for no solution. Yeah.
What do you mean by the size of the equation?
What number of bits it takes to write down the equation. Okay, I can write that equation down in a few inches of slide space. But what if the values of x, y, and z that are the solutions, you know, won't even fit on the slide? Consist of trillions of digits, which they could. You can write a simple equation whose solution is, where the solutions, the x, y, and z values, are trillions of bits long. Yeah?
I just don't understand, because if they are trillions of bits long, that would be the size of your input.
No,
So that,
no, this is the input. The verification algorithm has to be polynomial in the size of the problem instance, not in the size of the proposed solution. So you have to be able to verify a solution in polynomial time in the size, you know, where n is the size of the input to the problem in the first place. Yeah.
So why couldn't you just design a computer with like a trillion bit integer registries and then just...
Fine, then I'll give you the trillion squared. Numbers that are even bigger than that.
Numbers are in binary, right? Not in like unary where we can...
Yeah, I'm not talking about unary. So anyway, you know, that's not typically, you know, problems from NP. The solutions are, you know, the same order of complexity as the problems in the first place. Okay, so that's why it's not a member of NP. Why can't it be solved at all? I can think of an algorithm to solve it. How would you do it? What if it was a caddis problem? How would you try it? Yeah?
Generate permutations of integers and just...
Right, you try all possible triples of integers, right? Right, you know, write up one loop that iterates x through all integers. Maybe it goes 0, 1, minus 1, 2, minus 2, 3, minus 3, 4, minus 4. Systematically tries all values for x. Then have a nested loop that tries all values for y, and a nested loop that tries all values for z. And it runs until it, you know, for each combination, it evaluates the equation, sees if it holds. If it does, it's found the solution. Just need a big integer package and enough time. So why am I saying it's impossible? Yeah.
Because it's possible there's no solution.
It's possible there's no solution, and we've got to report that in finite time. And what I just suggested to you, if there is no solution, you'll never find that out. The program will just run forever. So it's been proven that there is no way, in general, to solve this problem. Yes, if there is a solution, you can write an algorithm that finds it. The problem is an algorithm that will discover that there is no solution in all cases. Yeah?
So the algorithm you're describing has nested for loops that will come to an end, so
No, they won't come to an end
why won't they come to an end?
because we're iterating over all integers, an infinite number of integers.
Why is it an infinite number of integers?
There are an infinite number of integers. I'm not talking about machine ints. I'm talking about mathematical integers. We don't know how large x, y, and z are going to have to be to have a solution. Right? So we just have to keep going. Now I haven't, what I've said isn't a proof that this is unsolvable, but I'm giving you an idea why it's unsolvable. Okay? And sort of the more famous impossible problem is the halting problem. And that problem is, what that problem does is it looks at a program and its inputs and says whether or not it will halt on those inputs.
So it's like a debugger.
Okay? So how would you solve, if someone said, give me a program that will solve the halting problem, right? It would have to take, imagine it's a Java program. It takes another Java program as input and says whether or not it'll halt when it's run. How would you implement it? Yeah?
I just want to clarify, is this like testing all possible inputs to the program?
No.
Is it just one set of inputs?
No, one set said, here's the program, here are its inputs. Will this program halt when it's run, yes or no? Yeah?
So couldn't you, are you asking like how you would implement it?
How would you implement an algorithm? How would you implement a program that solved the halting problem? Yeah?
The only way I can see it is run the
Right. You could take you're given a program and some inputs, and you ask, will this halt when it's run? So you run it. And if it halts, you report, yes, it halts when it's run. But what's the problem? Yeah?
And then just go infinite.
Right. How do you say that it doesn't halt? You'll never know for sure if it's not going to halt. It's just going to, so you'll never give an answer because you just run it and you'll never see it not halt. So now you have to try more sophisticated techniques. Maybe instead of, your debugger, your compiler will tell you sometimes you got an infinite loop. If you write while true and there's no way out, you might find out there's an infinite loop. There are lots of cases where you could just stare at the code and decide, you can do that. You can say, yeah, this is an infinite loop, this program will never halt, this is infinite recursion, it will never halt. But it's been proven, and it's not hard to do the proof for this problem, that can't be done. In general, you can't tell whether or not a program is going to run forever. Some cases you can, but in general you can't. So this can't be done. Yeah?
So this program so can you put itself as an input?
Yeah. So the halting problem is the classic unsolvable problem. Now, suppose we could solve a halting problem. Would that help us with this thing? So what we could do if we had the halting problem solved is what we would do is take that input instance, we would write a program that tries all possibilities to solve that equation, and then instead of running the program, we would just ask, does this program halt? If the answer is no, that program does not halt, we would just report, this equation has no solution. If we were told the program does halt, then we run it, and we'll eventually get the solution. So it would be a great utility if we could solve a halting problem. Yeah?
So is it the case with all unsolved problems that one part of the output is just impossible to use? It would take them time to figure out, like for the first one, obviously it would be hard to find out if there was no solution, and then the next one, it would be hard to find out if there was a solution.
Yeah, in both of these cases, the problem here is what happens, the obvious solution fails because what happens when there is no solution? The obvious program is going to run forever. Same thing down here. The obvious approach is just to try the program to see what happens, but if it runs forever, you're stuck.
So is that a general thing over all unsolvable problems that they're?
No, that's
just like.
Yeah, sort of, but that's not how you prove problems are unsolvable. That's just a way that you gain some intuition about it. Yeah?
Are unsolvable problems like NP complete where you solve one, solve the rest, or is it just a constant?
Yeah, the same thing happens where you have this class of problems. These problems are what are called recursively enumerable problems, meaning you can, this one here, meaning if there is a solution, you'll eventually find it. If there's not a solution, you may run forever. And and then all these problems, if you could solve the halting problem, then you would have an algorithm for all of them. So there is sort of this parallelism between NP completeness and between non-recursive programs. Yeah?
So I'm just curious, this problem that is unsolvable, where did we first see it, or where was it created, or?
Well, the problem of solving Diophantine equations is just a classic problem from mathematics. Won't define integer solutions to equations.
So one day someone was like, I'm going to come up with something really hard that no one can ever solve.
Well, no. Probably. This may have, in fact, have been one of the, there was a set of challenges, right around 1900, mathematical challenges to find, I think one of them was to find an algorithm to solve Diophantine equations. And eventually, rather than finding an algorithm, it was proven that there is no algorithm. Now, like I've said before, this is sort of the story of 20th century mathematics, where a lot of the most famous results in 20th century mathematics are proofs that things can't be done. Limits to what can be proved, limits to what can be computed. That's basically what Turing did. So Alan Turing, among other things, proved that there are problems that can't be described with programs, can't be solved with programs. And the interesting thing about Turing is that he did this work in the 30s. So he proved fundamental results on the limits of computing before there were computers. Yeah.
Can't we solve this using like vector calculus?
You could solve them for real numbers.
For the numbers?
You could come up with floating point approximations of the solutions. But, to solve exact solutions over the integers, no, there's no algorithm. It's known that there is no algorithm to do it.
Are you gonna give us more problems? Are you gonna give us more problems that can be solved?
No, that's, I'm going to stop there. Yeah?
Sorry, one of these could be solved, does that trickle down into the NP complete prompt solved?
Well, no. You can't, you can't solve these problems. Yeah?
What about, are any modern day quantum proposed solutions or anything quantum going on in regards to these problems?
I have never read any relation between this and quantum computers either, but that doesn't mean much. Okay? So, in addition, these are problems that are just, can't be done. There are also problems that are not members of NP, but which can be solved, but which have been proven to require exponential time or worse. So, there are all kinds of classes of problems. NP complete, NP and NP complete and P are sets of problems, but there are theorists have named lots of sets of problems that have different characteristics. For example, I told you that linear programming, that problem is actually P complete. Right? Meaning any problem that you can solve in polynomial time, you can solve with linear programming in polynomial time. Okay, so we've defined NP completeness. Now we're faced with the fact that there are lots of NP complete problems, and we need to write algorithms for them. FedEx isn't going to stop delivering packages because they can't determine the absolute optimal route for their trucks to take quickly, because that would require solving the traveling salesman problem. So they got to do the best they can. My larger point is, people try to solve, deal with NP complete problems the best they can all the time. And there are various approaches. Some problems have special cases that can be solved efficiently. Some NP complete problems have special cases, so you might just concentrate on the special cases. There are approximation algorithms for some NP complete problems. There'd be a problem that you can't solve, in general, you can't solve it exactly and quickly, but you can find an algorithm that gives an approximate solution quickly. And that's good enough if you're delivering packages, for example. You may not find the absolute best route that saves the most gas, but you can come close, let's say. And then there are two techniques for dealing with search problems and optimization problems. Search problems, you use backtracking, intelligent backtracking. Optimization problems, exhaustive search.
Slideshow.
Now, what I want to do, I could sort of step through it in a particular order, but I'm going to skip ahead. We'll come back and talk about backtracking. I want to talk about optimization problems because you've got to start working on your caddis problem or something. Okay, so branch and bound. In fact, I'm going to show you recursive branch and bound. All right, branch and bound is a technique that you should use. I recommend you use for doing this TSP problem, this final caddis problem. So let's think of what is the brute fortiest, anyway, the most brute force approach you can think to solving the traveling salesman problem. So let me just remind you what it is. You've got a graph. In the case of the TSP problem on caddis, the graph is known to be complete, meaning there's an edge between every pair of vertices, okay, which makes it bad for the traveling salesman problem because there's so many possible. It's no problem at all. No matter where you go, you can find a circuit. And finding a Hamiltonian cycle is no problem. You do it with your eyes closed because there are no missing edges. Put the vertices in any order, and that'll form a cycle. The problem is, since there's so many cycles, what's the smallest one? What's the smallest weight cycle? That's the traveling salesman problem. So, what's the brute force approach? Yeah.
Enumerate all the permutations and find the minimum.
Right, you find all the permutations. So basically you start somewhere, start at vertex A, and you try going to B. So you go from A to B, you make a recursive call to close the loop from B back to A. If that, and you find out the best you can do with that. And then when the recursion returns, now you instead of going from A to B, you go from A to C. And then you try A to D. So you're constantly backing up and trying a new direction. And you do that recursively. So the organization is going to look like this, roughly. So you're trying to minimize the solution to some problem. So you start with the initial problem P0. P0 is solve the traveling salesman problem for this graph. In the case of TSV. We'll ignore the best so far right now. We call optimize of P0, and if it didn't find a solution, report failure. Otherwise, we report the answer. So think of best so far as being the variable that's going to contain the answer at the end. So initially, best so far is infinite. We systematically, in this method here, we systematically try all possible routes, all possible paths, all possible cycles. As we close each cycle, we figure out what its total weight was. If it's better than what we've seen so far, we remember it. When we're done, we found the best solution. And so the programming comes down to actually the very simple problem of enumerating all the edges. Very simple recursive function. Okay, now let's think about what it takes to optimize. We've got a problem to solve. Initially, it's P0. So you've got a problem to solve. You look at the problem and you say, is this a complete solution? Well, initially, P0 is not solved. What I mean by complete solution is if you reduce the problem to nothing, meaning you solve the problem, then you update best so far. You see if your subproblem is a solution, you see if it's better than the last best solution you have, if so updated. Otherwise, you've got to expand each subproblem. You expand P into some subproblems and you explore each one in turn. So what that would mean is, let's say your initial problem is to start at A and find a path back to A. This is a vertex. The subproblems would be go from A to B and then find a path back to A. Go from A to C and find a path back to A. Go from A to D and find a path back to A. So those would be all the subproblems. So you recursively solve them. So your program consists of, in terms of traveling salesman, of a loop that's trying all the paths out of your current vertex by making a recursive call. So a recursive call inside of a loop. This is what makes it possible to do it efficiently. And I'm going to show you what I mean. So here's a graph, traveling salesman problem. So you write a program that, say, just picks a starting vertex, and that's going to be A, and tries to find the best cycle that starts at A and ends at A, and this is every vertex once. So in this graph, the unnumbered edges all have weight 1. So we could write, like I said, you could easily write a recursive program that exhaustively tries all ways of getting through this path and getting through this graph in a cycle and finds the best one. Let's see if we can do a little bit better. So this technique is called branch and bound. Suppose that we have already got A, B, and C. We've grown our path. So A, B, and C, and we're trying to now close the loop. I want to put a lower bound on how well we can possibly do. Before I try to solve the problem. Now, why would that be useful? Why would it be useful to come up with a lower bound? We know we're going to go from A to B to C. Yeah?
Once you hit that as your base case, you can stop,
Well,
better.
we don't. It's not that we hit the base case.
Or
Suppose I told you that, okay, if we start with A, B, and C, you're not going to do better than 10 or 14 or something. Yeah?
Doesn't that let you look at a different path that's at least 2 edges deep? That perhaps is a...
Well, but what specifically you do with the information? Yeah?
You fast forward to 10, 14. You fast forward to your lower bound, so you don't have to compute everything from 0 to your lower.
Yeah, sort of, yeah.
If you ever pass, 10 or 14, you can just quit looking, right, for that specific.
Okay, suppose that you've already found, remember the way this works is, you are trying, it's going to find some path back to the start and see what it's worth. Then it's going to back up and try a different way. It'll try all the ways out of the last vertex. Then it will back up to the one before that and try all the ways out of that. Systematically, it'll find every possible path. Each time it closes the path, it'll see, is that better than the last best solution we found? And if so, it'll update. So suppose that you have already found a path of length 10. And now you back up and you're trying A, B, C, and someone says, you know, if you go forward with this, you're not going to do better than 14. What can you do with that information right then and there? Just say, okay, I won't try. So rather than try and fail to do better than 10, if you know that you're not going to do better than 14, you back up from, you try a different way out of B, because the way you're trying isn't going to lead to success. The question comes down to, how do you put that bound on? Yeah?
Out of the weight of the edges, just hard.
Well, you certainly use the weights of the edges. So for example, let's go from A to B to C. Okay, we've already spent 3 units getting from A to B to C. How many more edges do we have to add to close this thing? Actually 6, right? We've got to go, let's say we went from D to E to F to G to H and back to A. That would be 6 edges. So we know that we've got to add 6 edges. We know that each of those edges has a weight at least 1. So quick bound would say, okay, 3 for the edges we've used, 6, a minimum of 6 for the ones yet to be used. We can put a bound of 9 just like that. Okay? So branch and bound is you're constantly estimating, not estimating, putting a lower bound on how well you can do if you go forward. If that bound ever becomes higher than the best solution you've seen so far, you bag it right then. You don't have to do a bunch of backtracking. The earlier you can prune, the better. Okay? And so your TSP algorithms are just going to come down to implement branch and bound, or actually implement exhaustive search, and then improve it by, each time you get to a new vertex, estimate how much it's going to cost to finish, and if it's going to cost too much, don't explore any further. Back up, try a different way. Yeah?
Does it mean for all of our cats problems, every node is going to touch every node?
Yep, every node is going to touch every other node. So there's going to be plenty of choices of ways to go. Yeah?
Sorry, so I'm kind of confused on the difference between the lower bound and the best so far.
Best so far is a solution you have actually found. And it's an honest-to-God solution. The lower bound is just, it says if if the lower bound is 14, we're just saying that if you continue, you're not going to find a solution that's better than 14. You may not even get one that's as good as 14. So if the lower bound is higher than the best so far, it's pointless to continue. You need to back up and try a different way. Yeah.
So with taking an approach like this on our last caddis problem, would that be faster than the dynamic approach?
No. No. In the last caddis problem, yeah, exhaustive, it would take an exponential time. Okay. So we have this. It's going to come down to how well you can put a bound on things. It's also, but it's not enough to have an accurate bound. You have to be able to compute the bound quickly. If you take a lot of time to get a really accurate bound, you haven't saved much time in it. You may have wasted time because you're spending all your time estimating and not enough time searching. So you need quick and effective ways of doing this. Now what I'm going to show you is sort of a classical technique to do it, but I don't think it'll work. In fact, I know it won't work for you very well in practice. It's got some improvements. And this is the bound. We take what we spent so far, which is 3, that ABC distance. We take, we compute the minimum spanning tree that hooks all the unvisited vertices together. Okay? Why minimum spanning tree? Why do we compute the minimum spanning tree of D, E, F, G, H? Why do that? Anthony?
You're gonna have to visit all of those nodes. And
Right. There's going to be, if we solve the problem, there's going to be a path that connects D, E, F, G, and H together. That'll be a piece of the solution. It'll visit them in some order. Among other things, that path is a spanning tree. It connects all the vertices together. And it can't have a weight any smaller than the minimum spanning tree that hooks all these vertices together. So we take the known cost, A, B, C. We take the minimum spanning tree that hooks those things together, D, E, F, G, and H. What else do we need to add in? Yeah?
the lightest edge from C to the minimum spanning tree, and the lightest edge from the minimum spanning tree to A.
Right. We gotta hook the path ABC to the minimum spanning tree. So we take the lightest edge out of A out to one of those, and the lightest edge from C out to one of those. Add those together, that's our lower bound. Now, here's the problem. Yes, we know an efficient way to compute minimum spanning trees, but it's too expensive to do every time you push out to a new vertex. And so to make this really fly, what you have to use are what are called incremental algorithms. An algorithm that takes a minimum spanning tree that you've previously computed and modifies it. So as we explore out, let's say we have a minimum spanning tree for H, G, F, E, and D, and then we take D, we decide to go from C to D. So now we need to shrink the minimum spanning tree. So you need to have an efficient way to take the larger minimum spanning tree and shrink it down. So I don't recommend you use this technique. This is to illustrate branching bounding. You need to find cheaper ways of doing the bounding, and we'll talk about some possibilities. Okay, so let's see how it would work. We're going to take the distance of ABC, the lightest edge from A to one of the out vertices, the lightest edge from C, and the way the minimum spanning tree would be. So let's start at A, and first thing we'll do is I figured out that right off the bat, there's a bound of 8. So where'd that bound come from? Yeah?
To create a cycle, you must have at least 8 edges, and the minimum weight of an edge is 1.
Well, but I'm using the minimum spanning tree approach.
Oh,
Okay? So, right, so there's no, A is by itself, so that's 0. We take the lightest edge from A out into the forest, and that's 1. And the lightest edge, another lightest edge out from A into the forest, that's another 1. So that's 2 so far. Then we compute the minimum spanning tree of B, C, D, E, F, G, and H. And it turns out that's 6. Can you see how to hook them all together with what's called 6? There's 7 vertices. So like we hook B to E, E to F, you go B, C, D, G, and then B to E, B to F. So that gives us
E to F.
E to F, yeah. That gives us 8. That gives us 6 for the tree, 2 for the edges connecting A to the tree. Okay? So we're not going to do better than 8. So we go try explore to B. Okay? What's the bound now? What are the components of the bound? Yeah?
So wouldn't it be the weight of the vertex connecting them?
Okay.
And then whatever's left would be 1 more?
All right, so 2 plus 1 for getting from A out to the white vertices, and 1 from getting B out to the vertices, so that's 4. And then the weight of the tree for those 6 vertices.
5.
Okay? So how can you cook together all those the cheapest way possible?
How you hooked A to
So just concentrate on C, D, E, F, G, H. Yeah?
You already found it for A, so you can just remove B from spanning tree for A, and then
Yeah, but let's not try to do an incremental algorithm in our head. Just look at it anew and tell me what's the cheapest way to hook all those white vertices together. Yeah?
You want it's 6, right? That's the cost.
I think so, yeah. So we can take C to D, that's 1. D to G is 2. G to H is 3. But now we have to use one of those edges of weight 2. That's 5, and then the one between F and E is 6. So we got 6 plus 4. So we got a bound of 10. So in the interest of time, we'll stop trying to calculate these things. You just have to trust my numbers. If we go from B to C, it turns out the bound is still 10. From C to D, the bound is still 10. Do our bounds do us any good at this point?
No.
No, because there's no, you got to have a best so far to compare them against. So we could just not compute them until we actually find a solution. Okay? If you go to E, it turns out now the bound is 11. You go to F, 11. You go to G, 11. You go to H, that's actually a solution, and it's 11. So now we have a benchmark.
We have to get back to A.
Hmm?
We have to get back to A, right?
Yeah,
11 includes the last.
well, the 11 includes getting to A. All right, so now let's back up to G. Is there another way out of G that we need to explore? It has to go, we have to find an edge out of G that goes to a white vertex. No. A way to explore out of F.
No.
Now in your program there's always going to be other ways out because there's so many edges. There's not another way edge out there, but there is another way to explore out of D. We could go to G. So let's go to G, and that bound turns out to be infinity if you do it, because it's just going to turn out there's not a spanning tree that connects F, H, and E together. So that infinity is bigger than the 11 that we know. So we don't keep trying to go out of G, we back up. Okay, we go from C to H now. And it turns out, if you do the math, there's a bound of 14 at this point. That's worse than the 11. So we don't have to keep looking out of H. We prune it immediately. So you can see how this wins.
Wait, sorry, are you comparing the 14 to the end of the other spanning tree?
This is a lower, if we continue in this way, we can't do every 14. We already know there's a way to solve it in 11. So don't do it. Give up on that. Try a different way. Oops. So back to there, we try E. It has a 10. So we try D. That turns out to be a 15, so heck with that. Try F. That's a 10. That's a 14. Bag it, and so on. So you end up pruning a lot of stuff out the bottom. So the question comes down to, what's an effective way to do the pruning? Okay? So the way I suggest you start this problem is just write a brute force traveling salesman problem solution. It's going to essentially, as efficiently as you can, try all the possibilities until you find the shortest path. Then it's trying to add strategies, then add branch and bound. So let's in a couple minutes here, let's talk about some easy ways to put a bound on a partial path. It's always going to be the cost of the path you have so far, plus some more stuff. What could you do? Yeah.
In terms of finding a Hamiltonian cycle, because you have like a set of vertices that you've already visited.
Mm-hmm.
So you have the weight of your path so far, plus the number of vertices that you need to visit.
Okay.
There's going to be a number.
All right. So all the edges are positive. So you know that, and they're integers. So you know that if you've got 6 vertices left to visit, the cost is going to be at least 6, right? So that's one thing you can do. Just the cost of the path so far, plus the number of vertices you have to come. Can you improve on that? Yeah?
In the traveling salesman problem, are all the edges the same way, or are they?
No, they're all different ways.
That's not.
So what would be better than just saying every edge will be at least 1? All the missing edges will be at least 1. Yeah?
Can we get an average?
Well, don't we go to averages? We got to have lower bounds. Yeah?
You can look at the actual weights out of that vertex because they're readily accessible.
Okay. So you could say, okay, 6 vertices yet to visit, or 6 vertices to find edges out of. You could say, okay, let's figure out what's the lightest edge out of each of these vertices. Okay? That would be a better bound than saying 1. I mean, a better bound would be just figure out you can pre-compute the weight of edges in the graph, and you could just take the 6 lightest remaining edges. It's not hard to think of ways to put bounds on the path to come. The trick is coming up with a technique to do it that's fast, and which is effective. It's a trade-off. Fast and effective. And your basic search code that's exhaustively searching needs to be efficient. So you got to think about efficiency. Yeah.
Should we assume that there is a solution for test cases?
Oh, there's definitely going to, yes, you can assume there's a solution because the graphs are complete. There'll always be a cycle, so there'll always be a lattice cycle. Okay, one more, and then we'll stop and revisit this next time. Yeah.
The question on Caddis, do we have multiple threads on Caddis, or is Caddis a single?
It still counts CPU time.
It'll count the CPU time.
All right. So think about this some, and we'll revisit it next time. Ways of coping with NP-complete problems. And two common techniques are backtracking, intelligent backtracking, and branch and bound. Backtracking is appropriate when you are doing a search problem. You just need a solution. So you try to go toward a solution. Sometimes you have to back up and try again, and eventually reach the solution, and you're done. Branch and bound is appropriate when you got to find, for an optimization problem, where even when you find a solution, you still got to back up and try again to see if you can find a better solution. So I'm going to start today by showing, first I'm going to show you some code examples of this stuff in action, and then we'll move to talking about the abstract. Okay, so this is a C# implementation of a 3-sat solver. So let me start by running it, make sure I got everything initialized the way I want. Do something small like 5 variables. So what this does is it creates at random, it creates a random formula. So what I've told it to do is to use 5 variables, so it'll create 5 different variables. And then it will create 15 clauses. So let me run it and I'll talk about what I mean by clause. So,
You mean 15 mass terms?
so you can see up there that the 5 variables are x0 through x4. And remember, when you're in 3-sat form, it's the conjunction of these disjunctions. The disjunctions are the clauses. So the first clause is not x3 or x2 or x4. And the next clause is x1 or x3 or not x0. And those are all ANDed together. So that's 3-sat form. You can take any formula, of Boolean logic, and put it into that form. And so then what it does is it takes those 5 variables and it generates, in this case, I think it's 25 clauses to make a formula. And then it goes about trying to solve it. And you can see that it gave the solution there, that x0 should be true, x1 should be false, the other should be true. And it tells you that there's a recursive method that we'll look at. And it's telling us that recursive method was called 9 times in the process of solving this thing. Okay? So we don't always get so lucky. Okay, well, that was not, it's the same problem every time unless I change the seed. Okay? So let's do that. Let's change the seed. So we'll make the seed be 8. And I'll run it. And that time it took 13 calls to solve. Now, that's a pretty small problem, and we can increase the number of variables. So let's increase the number of variables to 25. What the heck? Okay, so now 25 variables, and so it gives 5 times as many clauses, so it would be 125 clauses. Okay, so that time it did 3990 calls and found no solution. So we're handling 25 variables okay. So let's try 40. Okay, so there's our clause. And you can see it's counting up the number of calls. So we seem to have come to a problem that's kind of big for it to solve.
And this is with backtracking?
Yeah. So it went almost 700,000 calls before it could discover there was no solution. Now, we had a talk here, I don't know if it was last year or the year before, by a researcher who had won the Turing Award. And one thing he talked about was research into solving this problem. It turns out that it's a problem that needs to be solved if you're doing program verification or hardware verification. Essentially, you can describe conditions that have to be true about the program in terms of predicate logic, and then you got to try to solve it. And you need a three-set solver. And he was saying that industrial strength three-set solvers could solve expressions like this that contain millions of variables, like 1 million variables. If the example was a practical example, if it was an example that actually arose out of a need that was created to prove something, but that formula is generated at random, the solver couldn't go above a couple hundred variables. Okay, or maybe it's a couple thousand. Anyway, it was a whole lot less. And so he was just talking about the difference between that often comes up, that you can come up with an algorithm that will solve these NP-complete problems pretty well if the problems arise in practice, but not so well if they're generated at random. And he felt that further research was needed to understand the difference between problems that arise in practice and problems that are generated at random. Yeah?
So does that mean what comes up in practice is not random?
Well, surely, yeah, what comes up in practice is not random, but what is it about the ones that come up in practice that makes them apparently easier? And he didn't know, he was just raising that as a research area. Okay, so we're right at the threshold of what this solver can do. Let me show you how it works, and we can see how to improve it. Okay, so the main method just generates the random formula, and I'm not going to go into the representation. I'm not really satisfied with this program. I mean, there are a lot of classes because you got a formula, and the formula contains clauses, and clauses contain variables, and there's a lot of code to represent things. But the fundamental solver is actually pretty simple. So one thing I do to try to speed things up is, rather than pass a lot of parameters, I just have some static variables. So I use global variables to avoid the overhead of parameter passing. Because if you're doing hundreds of thousands of these method calls, the cost of passing parameters can add up. So calls is just a number that tells you how many times a method's been called. That's what I'm displaying. Formula is the formula we're trying to satisfy. Now the formula contains variables. Some of them I call unbound variables, and some I call bound variables. So the unbound ones are the ones that we haven't, initially all the variables are unbound. We haven't committed to whether they're true or false. At some point, we'll pick a variable and say, let's assume this variable is true. At that point, it becomes a bound variable. So all the variables that are currently unbound are in the unbound set. All the ones that do have a value are in the bound set. And so to set things up, I create a unbound variable set that contains all the variables. I create a bound variable set that's empty. I set the formula, and if I set calls to 0. And that's in my constructor. And then I have the solve method that I call. So this is, of all the code, this is what illustrates backtracking. So let's look at how it works. We start by incrementing the call count. Then we check to see if the formula is empty. So there's going to be a base case in backtracking. And in this situation, the base case is when the formula is empty. So the way a formula becomes empty is as we proceed through the search, we're going to, like I said, make assumptions about variables. So we're going to do something like, let's assume x0 is true. Then we're going to look at the formula. If that assumption makes any of the clauses false, then we fail right then and there. Right? That assumption has led to a dead end, because you've got to make all the clauses true. If it makes some of the clauses true, but not all of them, well, if it makes some of the clauses true, we pull them out of the formula, remove them from the formula, making the formula simpler, which means that over time the formula gets shorter and shorter as we remove the true clauses, and eventually it becomes empty. So when it becomes empty, that's when we have succeeded. We're trying to remove all the true clauses we're trying to move all the clauses because they're true without ever having to get stuck because one is false. So there's our base case. So this solve returns true if you found a solution and false otherwise. Right? Now this is where we decide, this is where we pick a variable and start making an assumption about it. So I've got two ways of making a choice, and right now all I'm doing is that first choice. I am looking at the unbound variables and just picking the first one, basically picking a variable at random. Then what I do is, of course, I'm about to bind it, so I remove it from the unbound variable set, and I add it to the bound variable set. Then I make the variable true. I tell the variable, you are true. I then take the formula and remove all the true clauses from it. Okay? So that method right there is going to search through the formula, look at each clause, and remove all the ones that are true from it. However, if it finds that one of the clauses is false, it's not going to remove anything. It's going to return false. So this call will return false if there was a false clause found, in which case the formula is not changed and we skip this whole step. Or it'll return true if there weren't any false clauses. And it also returns as this out variable the clauses that were pulled out of the formula. Okay? So at this point, if we get to this point, we know that there's still hope. We're not stuck, and hopefully the formula has shrunk because we've taken out all the true clauses. Then we just make the recursive call. We say, is that solvable? And that'll either return true if further work got us to a winning point, or return false if it didn't. If it returned true, we return true. No need to keep searching. If it returns false, we undo the removal. So we put the true clauses back into the formula. We set the variable to false, because setting it to true didn't work. So now we try setting it to false. Do the same thing. We print out the true clauses, try to solve it. If that doesn't work, we add the clauses back in and unset V, so now it's unbound, and we put it back in the unbound set and return false. So this is a very typical kind of backtracking search, where you start with a problem. At each level of recursion, you produce subproblems, simpler subproblems to solve. So where are we producing the simpler subproblems to solve? Yeah.
True clauses.
Yeah, it's right here and right here. So we prune the true clauses. Well, the way we produce a subproblem is we pick a variable and we say, okay, assume it's true, prune out the true clauses, and recurse. So the recursion is now for a simpler problem. More of the variables are bound, and the formula may be shorter. Okay? In this case, there are two subproblems at each level of recursion, because we're just picking a variable and there are only two choices for it, true or false. So at each level of recursion, we pick a variable and set it true or false. How deep can the recursion go? Yeah?
Number of clauses.
It's not the number of clauses that governs the depth of the recursion. Yeah?
Choose the number of clauses.
It's not that either. Yeah?
Number of variables.
Number of variables. Because at each level of recursion, we pick a variable and bind it. So, after we bound every variable, it's going to have to be the case that either every clause is satisfied and it's true, or some clause is false. So you can't go deeper than the number of variables. Now, if you knew in advance that there were, say, 5 variables, you could write this without recursion. How would you do it? Yeah?
You try all 2 to the 5.
Well, yeah, but you try all possible, all 2 to the 5th ways of assigning true and false to variables. How would you do that systematically without recursion? Yeah?
Could you just kind of, I guess almost a binary sequence for each of the variables and just iterate through all the permutations?
Yeah, you generate permutations, or that's not the way, that works fine. That's not the way I was thinking of. Yeah?
If you assign each variable an index, give it iterated 0 to n minus 1. And so each of those corresponds to a bit in a number.
Okay.
So then you just go iterate through that number.
Yeah, so he's proposing a way to generate the permutations. What I was hoping someone would say is we could just make 5 nested loops. You have one loop that tries both possibilities for x0, another loop that deals with x1, another loop that deals with x2, x3, x4, and so on. Okay? If you had 50 variables, you could make 50 nested loops. So of course, we don't know how many variables are. That's why we have to use recursion. Because we don't know how many loops to write. You can't dynamically create the loops at runtime. So what we do is we take the whole problem, we choose some way to produce simpler subproblems, and we only have to produce 2 in this case. It's enough to produce 2. And we recursively solve the subproblems. That's the structure of backtracking. Now, what determines whether backtracking is fast enough? Yeah?
You're able to quickly prune out all the bad.
Okay, he said you got to be able to quickly prune out all the bad. The important word he said was quickly. You've got to sometimes you got to think pretty hard in order to make sure that these basic operations that you're doing over and over again each level of recursion are fast. So, for example, I made sure that pruning clauses out was fast. And I made sure that it gave me the true clauses back. It gives me the clauses that are given back, so I can put them back in at the end. Now, what would be another way to do the same thing? Suppose there was no method to put clauses back into the formula. What would we have to do pruning? All right, suppose we got to this point right here, and this parameter didn't exist. All we had was a method which removed the true clauses from the formula, just modified the formula. It didn't tell you what it had removed. Yeah.
You could make a copy and just remove it from that.
Okay. So what you'd have to do is make a copy. So this is a solution that often occurs to people. You take the formula, make a copy, modify the copy. So you'd prune out the true clauses, you'd make the recursive call, and then when you're done, instead of adding the clauses back, you would just throw away the copy, and then you would make a new copy and prune it. So you have to make two copy before every recursive call, and then you can abandon the copy. What I found, I do more of this sort of thing than you might imagine, because I'm interested in puzzles, and a lot of times when I can't solve a puzzle, I write a program to solve the puzzle, and this is the sort of thing you have to do to solve a puzzle. And the copying will kill you. Copying a big thing is going to be way more expensive than making a modification to the thing and then undoing the modification after the recursive call. So that's the pattern you typically see. Before the recursive call, you modify the thing you're solving. After the recursive call, you put it back the way it was. You undo the change. Okay? And when I'm solving a problem, solving puzzles with this sort of thing, what I do is I write the program and I see if it can solve the puzzle. And a lot of times it can't. It runs out of time, or I just get impatient. And so I just kill it and I think, how can I make this faster? How can I be more clever? And I just keep trying things until it works. Until it's good enough. You can never get it. In general, you're not going to get it as fast as you might want. It just has to be fast enough. Now, to speed this up, we could start worrying about how can we prune more efficiently? Or is there a better way to represent clauses or variables than I have done? And I wrote this a couple years ago, and I've forgotten all the reasons for why I structured the classes that represent various things as I did. But I remember I had to put a lot of thought into it. But let's not do that. Let's put some intelligence into the backtracking. Okay? So there's implementation tricks that I've been discussing. The big one being make a change, do the recursion, undo the change instead of making copies. Make sure that all these methods are as fast as you can make them. We won't go there. How do we make things, how can we apply a little intelligence? Where's the only place we could apply some intelligence? Yeah?
And which variable we choose to...
Right. Which variable you choose to commit to. Right? We're just picking one at random, basically. I've got a hash set, and I'm just taking the first thing out of the set. And who knows what that's going to be. what would be a better basis on which to make the choice? What would be a better way to choose the variable to pick on? Yeah?
Which variable appears the most?
Okay, he said which variable appears the most. That's a reasonable answer. Who can think some other strategies besides picking the variable? Why would picking the variable that appears the most work?
Because you remove as many true clauses as possible.
Because, okay, so then you're committing in lots of places, and the more clauses you're changing, essentially, the more likely it is one will become falsified, which is really good, because that completely eliminates the recursion. Or it will become true, in which case the formula gets shorter. What's another idea? Do you have your hand up? Yeah?
So you choose whether or not to set true or false first, so we can do an if statement and say we choose false first.
Okay, so he said instead of setting the variable to true and then setting it to false, you can choose the order in which you examine. You could decide, I think it'll work out. I think I got a really good chance of winning this game if I set the variable to false. So look at it first. Okay, we'd have to figure out some way to make that decision. Janelle, what were you going to say?
Maybe a variable that has equal proportion of true and not, like, to see if they can cancel each other out.
Okay, so maybe look for one where, instead of picking one that occurs once unnegated and 10 times negated, pick one that's 5 and 5. Yeah?
Choose variables that are in the same clause. Like, you choose, there's X, Y, Z in one clause. You would choose after X, which is Y, Y, Z.
Okay. Let me rephrase that. What about this strategy? Some of the clauses will have 3 variables, 3 unbound variables. Some of them are going to contain 2 or 1, either because that's just what they were at the beginning or because we've already bound some of the variables. What if our strategy was to pick a variable that was the only unbound variable in its clause, the only remaining variable? Basically, you have a 1 variable clause. Why might that be a win? Yeah?
You can fully evaluate that expression, so you're guaranteed to get at least one result.
Okay, so if a clause contains a single variable, let's say it's a variable x. Okay, if we set x to true, we're guaranteed at least that clause is going away. It's been satisfied. If we set x to false, the whole formula is false right then and there, and we avoid a recursion. And that is where you win. You win when you can avoid making recursive calls, because a single recursive call can lead to who knows how many other recursive calls. Now, what if there isn't a formula with only 1 variable in it? Choose one from a clause that has only 2. And if otherwise, we choose one that, we choose one at random, basically. Yeah?
Curiosity, why can't we enlist help with multi-threads? Be like true on one thread, false.
Oh, yeah, we could certainly, that would be the way to speed it up, too. We could make the program twice as fast, probably, just by the first level recursion, just launching 1 task for true, 1 task for false. Now, the problem of doing that at every level is you eventually, you're going to get more threads than quarters, because the number of subproblems doubles at each level. But yeah, we can certainly do that trick. Yeah.
Couldn't we also blend these algorithms so that once you're small enough, you just brute force the rest of it?
Yeah, I mean, you could. He suggested blending it so that you try to be clever about picking the variable for a while, but then you just brute force it at the end. Yeah.
How about memoizing it so you remember
Okay.
the clauses?
So lots of things we could try. I'm just going to try one thing. So right here is where I pick the variable. Right now, I'm picking the unbound variable, just the first unbound variable, which is basically picking at random. Here, I'm going to be intelligent about it. I'm going to choose the formula. I'm going to choose a variable, hopefully from a clause that only contains 1 variable. If not that, from one that contains 2. Otherwise, one that contains 3. Now, the thing about making intelligent choices, you need to do it efficiently, right? You don't want to have there's a trade-off. Maybe you can make a really smart choice if you spend a lot of time making it, but that's going to slow things down. And for all these suggestions you've made, any of them might pay off. They may all pay off. It's hard to know until you try it out. So what I have to do to pick more intelligently is I'll just change this to false. So instead of making an arbitrary pick, I'm going to make a smart pick. Okay? So 40, when I did this test case right here for 40, it took like what? 700,000? 243. I think that's astonishing. You wouldn't think it would make that much difference, but it makes a huge difference. Yeah?
So your intelligent choice was to pick a clause with the lowest number of variables?
Yeah, I find,
false.
right, I find the clause with the fewest number of variables, and I pick that variable. So I'm looking for a clause with one variable ideally. When I find it, that's the variable I use. Now that variable may be unnegated, it may be negated. But the reason it pays off so much is that either, when we're going to use true for, we're going to, let's say x is a variable. We're going to make x true and then we're going to make it false. One of those choices is going to make the clause false, which makes the formula call false, which avoids the entire recursion. So now, if we manage to do this at every level, pick a variable with only, a clause with only one variable, there's no branching. It's just recurse, recurse, recurse. Either to succeed or to fail. And so with, with that, yeah.
So you're checking whether or not the variable will make the clause false by trying first true and then false. Could you like try both of those before you recurse at all, so that you try the one that made it false first?
Yeah, I mean, you could do that. You could do it in either order if you have some basis, some reason for them to do it.
Yeah, just so that you can try the false one.
Yeah,
And then just,
you could do that. So we can go a little higher now. So I can go up to 100 variables. But keep in mind that this isn't like making it twice as hard. It's making it 4 times harder because the number of possibilities doubles just every time I increase this thing by 1. Okay. So in that 100 variables, it goes up to 14,967 calls pretty quickly and says there's no solution. Now this will, I'm not saying this is a miracle,
Or more.
but it's certainly better. So let's go up to 200. This probably.
Should we decrease the number of clauses too?
Yeah, I mean, we could mess with it, but.
This becomes easier and easier to solve a constrained problem.
Yeah, this is probably going to be too many for it. I'm only willing to wait for a certain amount of time. All right, so here is sort of a description of iterative backtracking in the abstract. So try to connect this to what we were just talking about. So you start with a problem. That's the formula with all the clauses. And you have a set of active subproblems. And initially it's just the top level problem. While that set's not empty, you choose some subproblem from the set. Okay? Now this is iterative backtracking, not recursive backtracking. What I just showed you was recursive backtracking. In my experience, iterative backtracking doesn't work. Maybe I just do it wrong. But let me just explain the difference. So we have a set of subproblems to work on. We take that, so the thing in yellow is where you can apply some intelligence. So we choose which subproblem to work on. Initially, there's just a top-level subproblem. Then we expand it into some smaller subproblems. Now, what's that correspond to in 3 step, the expand step?
Well, that's when you pick the variable.
That's when you pick the variable and produce 2 simpler subproblems. So you create those subproblems, and then for each subproblem, you test it and see, am I done? If so, report the answer. Am I stuck? If so, throw that subproblem away. Otherwise, the subproblem is interesting, you add it to the set. And you just loop on that until you either use up all the run out of subproblems, or you find a solution. So, what makes this? There's no recursion because we take the subproblems and add them to the set. What happens to that set over time? It gets bigger and bigger and bigger. And that's the problem I've always had with iterative backtracking, is the set of active subproblems gets too big. So what you can imagine doing is using a priority queue to contain the subproblems. And what subproblems would make it to the top of the priority queue? How would you decide that? Yeah?
Maybe do the smallest problem sizes first?
Maybe the smallest problem sizes first, who knows? You would have some way of comparing subproblems to decide which was the best candidate to use next. So that would be sort of a way of approaching this bailing out and trying something else. You'd sort of lose faith in the subproblems you're working on and something else bubbles to the top of the priority queue. But again, in my experience, the queue just gets too big.
How do you build your subproblems back into the original problem? Like, we keep breaking it down, but how do you build
Well, okay, so what happens in my 3-set example is, as I go down the recursion, I'm setting variables to true, to false, to false, to false, to true. When I hit the bottom and I've succeeded, all those variables are set. Okay? And all those variables are sitting in the bound variable set. At that point, I just return out of the recursions, and then I can look in the bound variable set and pick out how each variable is set. So it remembers its solution that way. Okay? So these are all places where you can apply intelligence, these yellow things. So this is what iterative backtracking would look like. So there's a 3-set example. That's our initial formula, our initial subproblem, our initial problem. And we pick a variable, we generate some subproblems. We can pick W. I guess W is one of only 2 variables in its clauses, in some of its clauses. So those are our 2 subproblems. Now, we've got 2 subproblems in our queue. We've got to pick one of them. So maybe we pick that one, and we decide to expand on X. Now we've got 3 subproblems in our queue, and we pick one to, we pick that one, let's say. All right? So we simplify if Z is false, we simplify if Z is true. Now, at this point, we're stuck. Empty parenthesis means we failed. That's false. So we would have, the way I wrote the algorithm on the other slide, we would have tested these and seen that we're stuck and basically discard both of these subproblems. So those subproblems aren't really in the queue. So we pick, there are only 2 remaining ones in the queue, so we try that and that. That one gets discarded because we're stuck. Now we pick that. Both of those were stuck. Now we've got one other subproblem. Oh, I guess I'm stuck on all of them because they're all empty. Okay? So we only considered 6 possible assignments this way. Right? So that's intelligent iterative backtracking. And it worked here, but lots of variables, this queue can become huge. Okay? Any questions I could answer about that? It's a lot of the same considerations go into making this work that go into the recursive version. Yeah?
So if there's no solution, then even the recursive version would try all solutions, but try all possibilities, right?
Well, okay, there was no solution, and we did not try all the possible truth values. Recursive version won't either necessarily. Just depends. If you're really unlucky and you pick the wrong variables to expand, you can end up looking at all the possibilities. Right? This is recursive backtracking, which I just showed you on the slide. This is the base case. If we have won, return the solution. If we have failed, return null. I was returning true and false, and the solution was stored in a global variable. Otherwise, we expand each subproblem and search it. So you're not able to, in the iterative version, you've essentially got a conception, you've got a tree, and you can pick your subproblem from anywhere on the fringe of the tree. This is recursive, so you're always concentrating on a current node. Now, we decide how to expand the subproblem, so we can be clever there. We can decide the order in which we consider the expanded subproblems. We can be clever about these tests. And so this is what that looks like. We try that, we say, okay, let's take W and make a recursive call. Then we say, okay, what if X is false? We make a recursive call. Now we say, what if Y is false? We get there. We try what if Z is true? We get stuck. All right? Then we back up to here. Try another way. We got stuck. We back up to there. We get stuck. We back up to there. We get stuck. So we go over here, and so forth. So the same sort of thing is going to happen. So in the iterative approach, the amount of space you need is proportional to the fringe of the tree. the leaves of the tree. In the recursive approach, it's the depth of the tree. And clearly, the depth of the tree is going to be the number of variables at most. And if you're just talking about a couple hundred variables, that's fine. The fringe could be, at worst case, 2 to that. That's why I have my doubts about iterative. Yeah.
Are there any opportunities to memorize this?
I'm sure there are opportunities to memorize it. For example, the traveling salesman problem, when you solve it, there is a dynamic programming algorithm for TSP. But all it does is it turns what would be an n factorial algorithm with trying all the possibilities into an algorithm that's 2 to the n times n squared. So it's better asymptotically, but it's not like you've come up with a polynomial time algorithm. Now, you may notice, if you look at the leaderboard on the TSP problem, the top solution is 0.02 seconds, which is 40 times faster than the second place solution.
Who is it, Joe?
Yeah.
It's this guy named Sam that I know. But I happened to see him yesterday, and I asked him about his solution. He said he tried the CARP algorithm, the n squared 2 to the n, and it took about a second and a half. And so he abandoned that, and his solution is just, it's just branch and bound. And he was trying to explain in the car to me what all his tricks were, and he thought about it pretty deeply. So.
Is he going to release his code?
Yeah, he's not going to release his code or his tricks. But. Okay? So, anyway, that's Backtrack. It's a really good pattern to know. And the basic pattern is, you got a problem, you create subproblems, and you recursively solve them. And what often makes all the difference is, you don't want to make copies of the problems. You're going to take the problem, modify it, make the recursive call. When it returns, unmodify the problem, and then try the other direction, rather than making copies. So setting things up so you can efficiently do and undo changes is a big win.